3D coordinate systems. First, let's ask a simple question. Do we know what a coordinate system is? Okay, what is the simplest coordinate system that you can think of?
Origin.
Origin, a single point. So a point, and if you have to put a dimension, one might say, well, a point still has dimensions, but in a very abstract way. When we add a dimension, we are adding a variable. So if there is no variable at all, you can call this the zero dimension. Yes, just nothing there, it's just a single point. Now, when I add a variable, simplest variable that you can think of in math, x. I can't even draw a straight line. Okay, so I have 0. One variable. How many dimensions do you see? One. Just one. If you build it up, what is naturally the next step? Y. Y. Right? So you have 2 dimensions. Before we go to the next step, let's forget about that. In one dimension, say I want to give a value, a number. How would you write it? Say the number 2.
Just x equals 2.
X equals 2. Do we agree? X equals 2. A point on that one dimension. And you go to 2 dimensions, naturally, one varies with another, you end up having functions and all that stuff. If you want to refer to some number over here, what would you use?
Ordered pair.
An ordered pair. Enlighten us, Chris. What is an ordered pair using fancy words?
Ordered pair is when you describe a coordinate using parentheses, commas, x coordinate, comma, y coordinate.
Very fun of what you said. Can you hear? So if I pick a point P, 2, 4, x1, y1, 2 values, 2 dimensions. First dimension, x. Second dimension, y. Why do we call it an ordered pair?
It's in order from the letter ordering.
Ordered, letter ordering. Well, what if I call this x3, y4?
Yeah, order.
The pair part is easy. Okay, points. Why do we call it an ordered pair?
Describes a pattern.
Every single point is in order. Real number line having natural ordering. So the pairs move in order. This graph has a name.
Cartesian.
Cartesian what?
Coordinate plane, Cartesian plane.
It's a Cartesian plane. What's his name? Rene Descartes. That's where the name comes from.
Oh,
So Cartesian plane, and the point that we have x1, y1, that has a name, a fancy name. What is that fancy name? In terms of, you would have associated that word with Cartesian, most often. Starts with the letter C.
Coordinate.
Coordinate.
Oh.
So you can call this coordinates. Oftentimes you would have heard it as Cartesian coordinates. So whether you call it a coordinate or you call it a point, one and the same. How do we evaluate these points? We know we have a real number line, and what letter do we use to denote real number lines? In math,
the notation,
the notation.
the R
Oh,
with the special.
the special R,
Yep.
I call it handicapped R, because it's got a crutch. So you have the real number line. How do we evaluate every point in the real number line? There is a name.
With a function.
Function, okay. Do you follow what I'm asking? Every single point in this space is obtained by doing an operation. That operation has a name. You're doing something between one R and the other R. X,
Slope.
Y. Okay. I'm going to do this unless it comes to you.
All real numbers.
Yeah, that's R, right? One corresponding to the x-axis, other corresponding to the y-axis. That has a name, that operation. It has something to do with Cartesian again.
The cross product.
Cross product. Some call it Cartesian product, Cartesian cross product. Good. So far I've spoken only in terms of, just pure math. How would things relate in practice? Who cares about this? As a statistician, I can immediately see a purpose for this. In terms of an application, I'm sure everyone here took 2023. Yes, and you might have done something called simple linear regression. Yes, so you had a bunch of points, X, Y data, and you tried to fit a line of best fit. So those two-dimensional points help us come up with the line of best fit. Whatever that we can do in 2 dimensions can be extended to 3 dimensions. Visualizing things in 3 dimensions is hard. Even for me. Some days I could draw a 3D cube really well. Other days I would struggle. So 3 dimensions, one can try and start follow, but beyond that point, things get hard. You can't visualize, but in practice though, you would have n dimensions. These days, n could be as large as 10,000, 100,000. Again, easy way to connect to real life. Let's say the number of characters a person used in a tweet at 9 o'clock this morning. Okay, how many users do we have? A lot, right? Hypothetically, let's say 2 million users. So 9, 27, 32, million people. So we have extended 3 dimensions in a way, this way, if you look at coordinate paths, this way. But if you have x1, 9 a.m. in the morning, 10 a.m. in the morning, 11 a.m. in the morning, some number 18, 32, same user to keep things simple, 32, 0, 9, And if I say I have 2 million users, my dimension would end up being 3 by 2 million. Yes? Not easy. If you look at those points right there, if I look at them as x, y, z, or x1, x2, x3, then I pretty much left these 2 dimensions, entered the 3rd dimension. 3 points. So if you even try to graph it, I'm going to draw a 3-dimensional space. You just see a cloud of points. You can Google a cloud of 3D points and plenty of nice pictures. Suppose I added another column. 9 a.m., 10 a.m., 11 a.m., noon. 4 dimensions. I can visualize this, I can't do that. But the beauty of things is whatever that we are able to do in 2 and 3 dimensions can be extended to n dimensions. It's pretty much is the concept or the purpose behind understanding 2 and 3 dimensions.
I read an article that said 4 dimensions are now being seen because now people are finding the depth of the shadows in objects. So I just thought that.
It's hard for us to visualize. I tell people I can sort of visualize up to 5 dimensions in a specific way. Imagine a cube that is moving in space. If you can visualize that cube moving in space, that is 4 dimensions.
Yeah.
Imagine the same cube that is moving in space and time, 5 dimensions. So I can sort of visualize up to those 5, but can I draw those 5 dimensions? No, it's not possible, at least today. Who knows what will happen next? So do we understand the purpose of?
I was just wondering if you could describe more about the cross product and like the, I guess more like the definition. Because I've heard the term used, but I never like actually.
Now later on, we will deal with cross product of vectors. And when we refer to cross product here, we are saying, I pick 1, 1, 2, 1, 2. I need to take algebra. And 2, 1. 3, 1. Right? We call it a cross product. One, 2, cross, 1, 3. And if you do it for all real numbers, I can't write this out, which is why I simply picked whole numbers. That's a simple definition of just a basic Cartesian cross product. Later on, we would do something with vectors, dot product, cross product. That definition is slightly different. So let's not confuse this with that yet. But do you see why we call it cross product? If you add another dimension, for instance, let's say I have 2 dimensions, 1, 1, 1, 2, 1, 3, 1, 4, and I simply do 1, 2, 3. How many dimensions do I have here?
2.
2. How many dimensions do I have there? 1. So when I do the cross product, I'll end up getting 3 dimensions. So I'll have 1, 1, 1, 1, 1, 2, 1, 1, 3, 1, 2, 1, 1, 2, 2, 1, 2, 3. Get the idea, right? I can also do R2 by R2 in the sense I could pick 1, 1, 1, 2, 1, 1, 1, 2. I can create 4-dimensional points. So that's what we mean by, cross product and getting the entire space. Moving on to 3 dimensions. Erase.
Thank you.
If you are a naturally talented artist, you might be able to do this really well. But I'm not that great of an artist. But I'll try my best. I can draw the lines. So we are going to simply start with X and Y. And that would be my 3rd quadrant. We do it this way so that we can visualize the stuff. Oops. But uses X, Y, and Z. A good way to also understand and think of the coordinate systems is to simply consider this room. If you look at each side, just the length of the side, then that would be 1 dimension length. Now, if you look at the entire floor area, which is a surface, 2 dimensions. If you look at the entire room as a whole, you are in 3 dimensions. I'm actually standing inside a 3-dimensional supposed cube. You are sitting inside a cube. Good. Did we draw the axes? Okay, so now I want to start with origin. Origin, same usual point. But when we write origin here, how many points would I have?
3.
3. 0, 0, 0. So there is a thing called right-hand rule, where we put the thumb up and visualize it this way, indicating z-axis goes up, positive, negative, negative, positive, positive, negative. Good. So positive infinity, negative infinity, so in a simple 1-dimensional setting, when I started, I said, oh, give me a value we said x is equal to 5. Then we moved on to two-dimensional setting. We had an ordered path. Now, let's go back to that two-dimensional graph for a second so that I can connect it to 3 dimensions. So the two-dimensional plane that we know of, if I fix one value, let's say I simply fix x to be 2 as a point, y is 0, yes? But when I say x is equal to 2, what goes through in your mind?
Vertical line.
A vertical line. Do we all agree? When I say x is equal to 2, I'm thinking of a vertical line. Bad artist. I can just move the point over. A vertical line. So that's what we call a lower dimensional subspace. If I said y equals 2, what comes to your mind?
Horizontal line.
A horizontal line. Good. Also, a lower dimensional subspace, you reduce the dimension from 2, and you're looking at what? If you have to write it as a coordinate path per se, how would you write it as a notation to represent all the points in that vertical line?
You'd say 2, infinity.
2, infinity. That would simply mean 2 at infinity, which is not realizable. So I want to express every single point on this line.
You'd say all real numbers, like the R.
Okay. I'll repeat the question. I want to specify every single point on that line using some notation. Did we take set theory? Do we know about sets? No. I don't want to confuse you with other stuff. Do you have any?
No. Do you just leave the other 2 as variables?
Getting closer.
Could you, okay, could you write 2, comma, y, epsilon,
Epsilon,
the handicapped R, as you said.
2, good. 2, y, and I could say y
Yeah.
is any real number, right? That becomes arbitrary. And if I want to write all points, if you want to express them as points, how would you do it here?
Just a function. Like, or
I
not a
want-
function.
I want to write them as points. Same logic, but I will write it as
X, 2,
x, 2.
X is all.
All real numbers. Good. I'll repeat that idea. Now, 2 dimensions, I reduced it. I came to a lower dimensional space, and that was 1 dimension. So when I first started class today, we called it a Cartesian plane. And when we went to the lower dimension, the plane became a,
Lower dimensional space.
okay, which is graphically a
line.
line. So we started with the plane, ended with a line. Now we have a 3-dimensional space. I'm going to draw a cube. If you move it to a lower dimension, what do you expect to get?
A plane,
A plane. Obviously. So if I drop a dimension, for example, let's just drop Z, the vertical axis. And if you draw the graph here, that's going to look like that. Yes, so it's like tilted, you're looking at it this way. So XY. That is the XY plane. In this space. Now, what would happen if you draw one
From here,
from here? From here, 3-dimensional. Will we still get a plane?
We'd have multiple planes.
We are going to have multiple planes, but the question here is, if I drop y, what would it look like, the graph?
well, just get a line.
I'm dropping y from this.
So then you would have X and Z planes.
I would simply have x and z. Yes? So I'm going to drop y. If I draw this, it is going to look like that. Do we agree? So that is the x, and that's z. That would be the x, z plane. You call it z, I call it z. I'm right.
yeah,
It avoids confusion if you think about it. You know, when you say z, c, try it over the phone, talking to someone. If you say z, it's easy. So are those the only two options we have?
there's Y and Z, as you said.
Okay, y, z. So to get that, what should we do?
Drop the X coordinate.
Drop the x coordinate, and you would simply get the regular xy plane that we know of. Yes, but with respect to the notation that we have, it's not xy, rather it is y, z. So that would be y, z plane. So the lower dimensional space, when you reduce by one dimension, you move from a cube to a plane. Now, Chris said it's a math major, physics,
Engineering.
engineering, there's a bunch of other math majors. Well,
I think it's just me.
it's just you, okay, I see why we need chemistry and why we need culture in chemistry. Isomers, organica. It crossed my mind yesterday, I didn't know it when I was driving home. So in math, beyond that dimension, we'll simply call them as hypercubes. So you have n-dimensional hypercube, n-1 hypercube, and so on. Hypersphere, we use it in spherical coordinate system. We'll talk about that later. So, good so far? Do we follow this part? So you should sort of, you should be able to visualize these planes right here. We have quadrants in Cartesian plane. Do we agree? Yes? Now, which one should we consider out of those three? I think the first one would be easy. the XY plane, based on the three-dimensional coordinate representation, has quadrants. Do you agree?
Yes.
Can you relate the quadrants that you see to this graph? Going to point, and you can tell me if it's right or not. That is this part, yes or no? Fully, entirely.
No.
No.
This entirely forms that.
No.
No. How about all of this?
Yes.
Yes. And the next one would be the plane there. All of that. Agreed or no?
All of it, yes.
So if you look at this part, it's all of that. And the next one, let's see, is it this? What's the word right here?
Just,
Is it just that?
No.
No, it's all of that. The plane is right here. And if I simply picked this part, what would that correspond to? Which one?
Quadrant on the YZ plane, right?
So first, out of those three pictures, this one will belong to the first, second, or the third. The third. Easier way to think about it, y-axis, z-axis, yz plane. So out of those three, we're going to be here. Which quadrant am I referring to? I'm referring to that. Good. And if I picked these two, naturally, I'll call it x, y. I have x-axis, y-axis. I have to look at the xy plane. Good. So visualizing might be a bit challenging, but I recommend that when you draw these two, you can draw straight, but that always is an unknown. Okay. Are we good so far? So that's the system as a whole. We have the word quadrant in 2 dimensions. In 3 dimensions, we have the word octant. Any idea as to why we call it an octant?
Because it's 8 parts.
It has 8 parts. I don't see 8 parts.
see the root oct, which stands for.
The oct stands for oct, octal, 8. 8 of something. I don't see 8 of anything in that book. Do you?
I think so.
What do you see 8 of?
There's 8 cubes.
There are 8 cubes. How would you draw 8 cubes? I forgot your name. What's your
Chase.
Chase?
I'm also a horrible drawer, but I can see.
Wow. I can draw a cube easily, right? But what about the octant? So I don't know how you draw a cube. This is how I learned to draw. Good. So that makes sense. 3-dimensional space, great. Where do you see the octant part?
So there's 8 cubes, each one has one and a side on each of the 3 axes. So there's one up here, there, and there's another 4 on the back section.
Okay,
Yeah, I'm seeing the same.
you're saying the same thing.
It's like 8
Um,
quadrants. It's like 8.
if you, huh?
It's like 8 quadrants.
8,
8 quadrants, but like they're not, they wouldn't be quad.
they're not quadrants, they're octants. Everyone would have played with this when they were young. It is a toy. Cube,
Rubik's
Okay.
Cube.
Rubik's Cube. One of the easier ways to visualize, but I'll try to draw here. It is not going to be the best, but I will try. Should have used a different color. but- Some might see it, some may not. Don't take it personally if you cannot. I'll use a different color.
I can't put this.
Sort of seeing it now.
I can sort of see it.
Sort of, okay. Just follow what I'm drawing, then you might be able to see it easily if this marker works.
Would you like another one?
Huh?
Would you like another marker instead?
I guess I'll make it. There is one more left. Where do you think it's at? Right here? Yes,
Driving through the middle one.
right. And if you sort of connect further, again, follow what I'm about to do. I'm going to draw sort of the first octet. There's one more in the middle. Someone mentioned it, so there has to be one like that. Yes? Okay, whole bunch of lines. I'm going to draw the first octet. With me? Okay. Hopefully this one. It doesn't, so follow, going to use red. Good. First octet. I'll do the second one, and then we can do the third and fourth. So to get to the second, I mean, of course, a line there too. Now I'm going to try to draw a second octet. This different color. Hard ink. I don't know what happened. Again, follow my hand and how I draw this stuff. So there. Second octet. Third, fourth, one behind, behind. 4, 4, 8. Good. So you have 4 cubes stacked, and you end up getting 8 octets in a 3-dimensional space. Those would correspond to the positive and negative parts of the x's and the y's. Yes? So if you start writing them out, if you place the origin here, you would say positive x or positive y, negative y, and then positive z, negative z, etc. So not a bad picture. I can see the first 2 octets really well. I should have given an artist. No. Okay, are we clear so far? Looks like you have a question. Do you have a question?
I always struggle with the geometric visualization, so it's just a thing I gotta work on. I see the first 2 octets.
So I'm just explaining this. As we move along, you can just forget about, drawings out. First bit, it's best that you can't. Okay, now, let's say 1, 2, 3, 4, 5. -1, -2, -3, -3, -5. 1, 2, 3, 4, 5. -1, -2, -3, -4, -5. 1, 2, 3, 4, 5. Same on this side. -1, -2, -3. Good,
I realized I had a question.
go ahead.
So with the x-axis, I know you said in the beginning, we used the right-hand rule and that showed the x-axis. I guess this way was positive, this way is negative. Was that just sort of a convention that was adopted?
convention.
Why do we adopt that the x is positive in that direction?
I think it goes back to history. Might be Maxwell. I think it's Maxwell. In terms of referring to fields, we had, right hand and then left hand, specifically magnetic electric fields. I have to look it up. So you have the right hand rule and the left hand rule. I think right hand is used as the convention in most cases. So it goes back in history. But, as mathematicians often do, this is fine, but of course we can rotate the coordinate system and name it a different way if we want to. In other words, you can switch axes. But it's just convention. Okay, now I want to visualize a point on the full. Let's say I move 2 steps along the x-axis, 4 steps along the y-axis, 2 steps vertical. So if you want to visualize it here, origin, 2 steps here, 2 steps there. I'm not going to go this way, we'll just leave it. So I'm right here somewhere. 3. I want to sketch that point here. Where should I start? Origin is a good place to start. So 2 steps along the x-axis, forward. I'm going to do positive, positive, positive. So 2 steps forward here, and 4 steps. Let me go forward this way. So 2 steps x, 4 steps y. How many did I say? 2. So 2 steps above. Well, that's fine. So from here, moving there, from there, I'm moving up there. So I am in space there somewhere. Yes, if you look at this plane, I'm somewhere above. Imagine yourself on a ladder standing here, and that would be that point. In terms of a coordinate, how would you write it? 2, 4, 2. Good. Now, there is the concept of projection. what does projection mean to you if you're projecting something?
Display.
Huh?
Displaying.
Displaying, okay. I'll just use this two-dimensional case. I'll pick a point, 2,4. Okay. I am going to project that to a lower dimensional subspace. Good. Now, that two-dimensional plane has y-axis, z-axis. So typical Cartesian plane. I want to project it to a lower dimension, which would mean I need to go from 2 to 1. Yes? How many ways can I do it? Projecting down to a lower dimension for that point, 2,2.
2 ways.
2 ways. What are the 2 ways?
We can drop. This is x comma y, correct?
Y comma z.
Or is that, okay, so we can either drop the z and keep the y coordinate, or drop the.
So-
y and the z.
I'm going to drop this way. Yes, in which case I would simply say 2. And here it is the axis, so I'll call it 2,0 because I'm on the axis. Or I can drop over here to this axis. 0, 2. If you think along the same lines, you can drop to a lower dimension here. Do you agree with me? So 2 dimensions, I have a point dropping down to this point 2,0. Of course, I can drop to any point along, say, an arbitrary line. Yes. Oh, it's vertical like that. If you extend that idea over here and you are dropping down to a dimension, where will you land? Easier way to visualize. Up there on a ladder, and I fall. Where would I fall?
Onto the x, y plane.
On a plane. Yes. So if I'm in space and I drop, I'm going to fall on a plane. I projected myself onto a plane. Fire exit. I'll be standing down, someone jumps, I would think, oh, he projected. It's a bad joke. Okay, so I'm going to sort of draw this. Let's say I'm projecting, dropping down. I will drop down to that plane. That projected point will have what coordinates? Will it have, you're going to drop one coordinate. Which one would you drop?
Z.
Okay, so there is no z here because you are dropping onto the xy plane. So you can write the point where you projected to as 2, 4,
0.
Good. So you can pretty much drop from space to a specific plane, but depending on where you drop, which plane you land in, you're going to simply get rid of that point. Good. So by all means, when we say projecting, we are projecting say a point from a higher dimension onto a lower dimension. But this is going to come up later. I haven't taken linear algebra yet. It will show up in linear algebra. Engineering has to take linear algebra also. So remember at the beginning I did the vectors, I'll touch up on that again. Projection will show up there as well. So I had 3 dimensions, drop down to 2. You can drop again and you'll get to 1 dimension. Let's say you projected or dropped to this plane right here. So at that point, I fell and I kind of stuck to this wall. Visualize that way. So standing up here, I fell, but I stuck to that wall. So I'm right here. Yes. So the point that was here got projected to there. And how do you represent that point?
X.
Huh?
The XZ plane.
Okay, so it would be X and Z, so how would you write it? So I had 2, 4, 2, I want to draw.
Wouldn't it be 2, 0, 2?
So I want to draw Y, so 2, 0, 2. Good. Let's see. Of course, I can drop onto another plane if I choose. But do you see the dropping part? So if I have a point here, I can drop down there. If I have a point again here, I can drop onto that axis. So anytime you're projecting, you're getting rid of that 1 dimension. Good, then you put it as 0. Now, instead of projecting down to exactly 1 point somewhere, let's say you have to have a set of arbitrary points projected on to this plane. In other words, so I'm here, I move on over there, move on over there. Let's say I'm moving my ladder little by little, and every single time I don't feel injured, so I climb back up the ladder, move, push myself down, fall, climb back up the ladder, push myself down. That's the case, right? So if I did that, I'm projecting myself for various values of, in that case, Y. Do you agree? I'm moving along. So needing to be just 1 single 0, you can land on a set of Y values. Do you agree? What do I mean by that? Instead of dropping straight down onto 0, you can land on another plane. In 1-dimensional case, if you drop down, you went to single point. 2-dimensional case, you drop down, you went to 1 point, should have said 0 points. Here, if I represent, or if I call Z equals 5, okay? That would mean I have Z to be 5, X and Y are free to roam. So what am I referring to? Am I referring to a line or am I referring to a plane? A plane. So I am fixing Z at 5, but I'm going to let X and Y wander. So X is over here, Y is over there. So wandering, oops. But X is equal, excuse me, Z is equal to 5. Yes? So when we represent, or when we say Z equals 5, we are actually referring to a plane that's going this way. When we refer to Y equals 5, we are referring to a plane that's over here. You draw it, it would look like I messed the drawing up, so this is the dark plane. And that leaves us with one case, which is X is equal to 2, you would draw it this way. Good. That way. You cannot become a surgeon or a surgeon without knowing this. Sure, you can kind of somehow do it at random, but you will get sued. You know, the lateral side, posterior side, anterior side. So it goes back to 3 dimensions. So when we refer to X is equal to 5 in 3 dimensions, or X is equal to 2, we're not referring to a line. We are referring to a plane because we are fixing X and letting the other 2 run. Good. Do practice a bit drawing this stuff. After this section, we're not going to get into drawing stuff, but you should be able to sort of visualize and connect to this.